In this question, it's going to be a rectangular core. So in this question, it's going to look something like this, where we have a rectangular cross section, and it just looks like this. It's just a bar. It's a rectangular bar. If I were to slice that bar, then the cross-sectional area would look like this if I just took a slice out of it. This is the area. I can say area perpendicular for cross-sectional area, or I can say area pi for cross-sectional area, because pi is our symbol for plane in math. So we can do that as well. I like doing that. But this is our cross-sectional area of a rectangular core. So it's a little bit different than if you have a toroidal shape. And quite honestly, it's a little bit easier. So here, mild steel has a relative permeability of 800. So let's look at what is given in the question first. We have a few things given to us. We have relative permeability, and I like to kind of write down what is known. We know relative permeability is 800. Relative permeability does not have units. I don't expect it to be. It is a ratio of the permeability of this mild steel to that of free space. So it has no units. Calculate the reluctance. So it's saying calculate the reluctance. So I would, of course, just say the reluctance is what I need to know of a mild steel core that has a length of 10 centimeters. Length equals 10 centimeters equals 0.10 meters. Because I'm in the magnetic circuits world right now, I know that all these formulas work in meters. So I'm going to convert that right away, is one of the steps that I take to solve these problems. And has a cross section of 1 centimeter by 1.2 centimeters. So this cross section up here is actually rectangular cross section, not square like what I drew it here. So it has a cross section of 1 centimeter by 1.02 centimeters. So area equals, let's just draw it first so that we know what we're looking at. If this is what it looks like, I'm going to exaggerate it a little bit. It's rectangular, and it means that this cross-sectional area here is 0.01 meters by 0.012 meters, almost square, but not quite. And that would be 1.20 times 10 to the negative 4 meters squared. And don't forget that that's meters squared, and we have to keep our proper SI units in these problems, or else we're not going to get the right units in the end. Now, I've put this in scientific notation because it's a very small number. You don't have to do that, but it does really remind you to do your significant digits properly. In this problem, I have 3 significant digits because there's 1, 2, 3 on permeability. Length is, I have 1, 2, 3 on length here. I'm going to keep 1, 2, 3 significant digits on cross-sectional area here. So I'm very comfortable expressing that as 1.20 times 10 to the negative 4 in scientific notation if I want to, which reminds me to have those 3 significant digits. These are measurements, so we should be mindful of our significant digits. Now, mean path length and cross-sectional area are the things that are more difficult in this type of question. So I just want to go over what mean path length means. It says the core has a length of 10 centimeters. What this means is that from the front to the back, if I were to take a line right down that middle, then that would be my mean path length, and that's what is 10 centimeters. Now, how do I know that's the mean path length? That's the length of this core, it says in the question, but why is that the mean path length? Well, it's the mean path length because So let's write it up here. Mean path length L. The reason we're saying mean is because it's like sort of the average, right? Oh, it's the average of what? It's the average of the travel that the magnetic flux has to go through. So it's the average length through the material that the magnetic flux lines travel. The average length through the material that the magnetic flux lines travel. So in this bar magnet, if there were an induced magnetic field in this bar magnet, then for sure those flux lines would be going like this through the magnet, and they'd be expanding in free space, right? Expanding out there and then coming back into higher density because they love this ferromagnetic material at the poles here. And this would have a north and a south pole would be created in this material. So these are my lines of flux of magnetism. So now if I ignore the lines of flux of magnetism outside of this bar magnet, and I look at just where they're traveling inside the bar magnet, and now I'm looking at these lines of flux, okay? I'm looking at all of these blue lines inside the bar magnet, and I'm asking myself, what is the mean path length? Well, in this question, I don't want to overthink things. And I'm going to say, okay, well, this line of flux, mean path length, went from here to here. This one went from here to here. It's the same. This one went from here to here. It's the same. This one went from here to here. So the mean, the average length of all of those paths is L from here to here. It's the length of the bar. So the average length that the flux lines travel inside the ferromagnetic material is the definition of the mean path length. And in this case, they're all traveling the same distance. They happen to all be traveling the length of this, what did we call it? Rectangular core, the length of this, this mild steel core. So they happen to be traveling 10 centimeters. Every one of them did. I didn't even take an average, okay? So I'm just looking at that middle length. So that's why mean path length is this. Cross-sectional area. Cross-sectional area is just the area of this little bar. So if you have a magnet in this shape, it's more straightforward than a toroid. So what we have to look for in the question is RM. And from here, we have to say, okay, well, do I have a formula for that? The one that I always remember off the top of my head is the MMF, right? The magnetomotive force over the thing that it is generating, which is the magnetic flux. But it is also equal to, which we have derived, length over permeability times mean path length over permeability times that cross-sectional area. And we have to just remember what permeability means. And permeability is the formula for permeability. We already know length. We already know cross-sectional area. We have to remember that the permeability formula is relative permeability is just the material permeability itself over the permeability of free space. That's a formula we have to remember. So if I were to rearrange that to solve for the material permeability, I can put that right here in this equation. So now I'm getting permeability is the same as multiplying the relative permeability times the permeability of free space. Let me just highlight where that came from so that we can see clearly that this is the equation we have rearranged. Oops. This is the equation we've rearranged that we have substituted here, what's in yellow. At times, that cross-sectional area, which we have already worked out. All right. Now we know the relative permeability is 800. Permeability of free space is a number. We know the permeability of free space. Permeability of free space is always 4 times pi times 10 to the negative 7 is a very, very small number. Webers per amp turn times meter, or per amp times meter if we don't want to carry the T for turns, but I like carrying it. It's not a standard SI unit though. I like carrying it for simplicity, especially when we are new learners to the magnetic circuit calculations. So I'm going to now substitute in my length, carrying 3 significant digits. I am going to substitute in my relative permeability, which is 800. Again, it's a ratio, so it does not have units. My permeability of free space, which by definition is 4 pi times 10 to the negative 7. I'm going to keep its units for clarity, and because we always ought to keep our units in every mathematical equation that we're solving. Our units help us. I'm going to write right over my area here, which is pretty bad form, but I am going to substitute in that very same thing, 1.20, 2 significant digits times 10 to the negative 4 meters squared. Okay, now I see that I have a meter squared here that can cross out with this meter and this meter, giving me 8.33 to 3 significant digits times 10 to the 5, pretty big number, amps. I like keeping the turns in there, per meter. And this is our answer. And this is the same thing that this textbook got here. So that makes us happy. At least there's that. So we have just taken this formula and we have substituted in, but in order to do that, we had to remember a few things. So let me just highlight those things that we had to kind of focus on here. We had to remember that that length is, that the mean path length is that of this path up here. We had to remember that that cross-sectional area is this cross-section here. That's that cross-section there. And we had to remember the relationship between permeability of free space and relative permeability, which was put in the equation here. So this is what I would consider a reasonably straightforward magnetic circuits problem.